Delaware Tech, Chemistry 100, Chemistry 110, Unit 5 continued, Reaction Kinetics and Catalysts. We've already talked about kinetic energy in Unit 2, and kinetics refers to movement. So reaction kinetics refers to the movement of atoms and molecules in collisions during the chemical reaction. So when somebody says reaction kinetics, they really mean the study of how fast the reactions actually go. So in order to study how fast the reactions go, let's look at a simplified system of reactions between gas molecules. So there's no solvent, there's no water present, there are no solids. It's just gas particles that are moving around in a container, slamming against the walls and slamming against each other. So there are a number of rules in this kinetic molecular theory that we assume. Now, these aren't all exactly true, but these are assumptions we make in order to simplify our understanding of how molecules or atoms bounce against one another and react chemically to form new products. So the first one is that gases are composed of large numbers of particles. Well, that makes sense. They can be atoms or molecules, and they behave like large spherical objects in constant random motion. Well, what does that mean? Well, you can think of them like little balls that are just moving around, bouncing around inside a container. And these particles move in a straight line until they collide with other particles or the walls of the container. So these balls are slamming against the walls of the container, and then they're slamming against each other. They're just bouncing all over the place. And we will consider that these particles are very small with respect to the container. That is, the vast majority of the volume of the container is empty space. The gas particles themselves don't take up that much room in the overall container. And we're going to assume that there's no force of attraction between the particles, and obviously there must be some interaction if you're going to have chemical reactions, but for now we're going to assume that these are just bouncing against one another and slamming into each other, and that there's no intermolecular forces holding them together that we would see in, say, a liquid or a gas, a liquid or a solid. And the collisions with the walls and with each other are what we call perfectly elastic. Elastic means that when you have particles with a certain amount of energy and they slam into other particles or the wall, no energy is lost. It might be passed from one particle to another, but we're going to assume the walls don't absorb any heat, and we're going to assume that if a particle slams into another particle, the energy is just shared between the particles or completely passed on to the second particle. And we're going to make an assumption about the average kinetic energy of all the particles. Remember, kinetic energy is the energy due to movement of these gas particles. The faster they move, the higher the kinetic energy. And it turns out that kinetic energy is directly related to the concept that we refer to as temperature. So while we think of temperature as a measure of hot and cold, a physicist or a physical chemist thinks of it as a measure of how much kinetic energy. In other words, the higher the average speed of a molecule in a collection of molecules, the higher the temperature. Higher temperature means more energy to react. So if you increase the temperature, they have a lot more energy when they're slamming into each other for the potential to chemically react. So let's talk about what these reactions look like when we're analyzing them as they transpire. Reaction kinetics, as I already mentioned, is the study of the rate of chemical reactions, how fast they go. Many reactions are actually complex, so there'll be part of the reaction will happen, and then another part, and then another part, and another part. And we look at individual rates, but for a course like this, we're just going to consider the overall rate of the reaction. And there are a lot of terms associated with looking at the rates of chemical reactions, as well as the energies involved in those chemical reactions. And the first one we're going to talk about is a concept called activation energy. Activation energy in most chemistry textbooks is abbreviated as E sub A. Sometimes the A will be capitalized. If you're looking at more advanced energy studies, sometimes in biochemistry, sometimes in biophysics, they'll use the abbreviation delta G, and that symbol is called a double dagger. So that's called delta G double dagger. We won't be using that in this class, though. And this is the minimum amount of energy required to initiate the reaction. In other words, it's the energy barrier to get over the hump in order to go from reactants to products. So let's look at this first diagram here on the left, and I'll label the activation energy of the one on the left, and we also can call this activation energy, or we can call it transition state energy, or the energy barrier. That's more of a colloquial way of describing it, but you will frequently hear transition state energy or activation energy. And this is the hump of energy that reactants need to, squeeze that back, this is the hump of energy that reactants need to get over in order to become products. There's always a hump, and that energy of the hump going from the reactants to the top of the hump we call the activation energy. So you can think of it like a skier on one side of a hill. If they want to get to the other side of the hill, even though the other side of the hill may be lower, in the case of the left diagram in red, or even higher, as in the case of the right diagram in green, in either case, you have to get over this hump in the middle, and there's no way you can get from one to the other without going through the hump. That hump is the activation energy. It's the energy that the particles must have in order to get over the hump and become products. And likewise, if products are going to go back to being reactants, they have a hump too. And you can see in the case of the left reaction, the hump is much, much higher going backwards, whereas on the right side, the hump is actually much lower when you want to go backwards. And that arrow should only come up to the top of the hump. So I'm going to erase my notes there. Oops, let's clear that. Not sure why this is not clear. There we go. So those are the activation energies. It's the amount of energy the particles need to get over the hump. And it turns out these determine how fast a reaction occurs. Why? Because remember, the amount of energy, and this diagram I forgot to point out, this is plotting the potential energy of the particles, all the particles of the reactants or the products, or somewhere in the middle, versus time. And we don't usually write it as time, though I wrote it as time here. We actually call it reaction progress. In other words, it's going from the beginning to the end of the reaction. So we refer to it as the reaction coordinate or the reaction progress coordinate. Sometimes you'll see it as time, but time isn't exactly right because these aren't evenly spaced. You might have part of this that's very fast and part of it that is much slower. But the point here is the taller the hump, the slower the reaction. This would be a slow reaction on the right. This would be a fast reaction on the left. Why is the left faster? Well, because many of the reactant molecules on the left have enough energy to get over the hump. Whereas on the right side, very few of the reactants have enough energy to get over the hump. So it's going to take longer for those reactions to occur. So the only thing that determines how fast a reaction is the activation energy, that height between the reactants and the activated energy state in the middle, which we call either the activated complex energy or the transition state energy. Or the transition state is the form of the molecules in the middle. And these transition states aren't like normal molecules. The reactants are like normal molecules or atoms. The products are like normal atoms or molecules. But the transition state is somewhere in between when you're in the middle of breaking some bonds and you're in the middle of forming other bonds. And that's very unstable, and that's why the transition state energy is so incredibly high. So you have to get through that. If you want to go from reactants to products, you're going to have to break some bonds, you're going to have to make others, and you have to get over that hump to do that. So that's the activation energy. It is what determines reaction rate. Low activation energies are fast. High activation energies are slow. In addition, we have another energy we look at, the difference between the reactant energy and the product energy. And that would be shown over on the right of both of these. It is the energy difference between the products and the reactants. In other words, if you took the energy, which we'll call H, of the products and subtracted out the energy of the reactants, we end up with some change in heat energy. So this is the energy that is either released or absorbed during the chemical reaction. And if in the left case, this is a reaction where the reactants are higher in energy than the products. That means the reactants are less stable than the products. Products are low energy, very stable in the red case, on the left. And in this case, this is a reaction where if you're going from the reactants to the products, your energy drops. Well, that energy has to go somewhere. Well, the energy gets literally released as heat. So heat is generated. And if you take the formula I showed you, this is the heat, this would represent the heat of the products, this would represent the heat of the reactants. If I take a small number minus a bigger number, I'm going to get that my change in H, a change in the heat energy, is negative. So in the left reaction, heat is being produced, and the change in heat, the delta H, is negative. We call this reaction exothermic because heat thermic, get that a little bit better. Pens are not writing very well. Let me clear that a little bit. Actually, I'm going to clear a lot of this. Exothermic means the heat, and exo means out. So the heat is literally going out. The heat is going out. And these reactions feel hot to the touch because heat is coming out. Most chemical reactions that you're familiar with produce heat. They get warmer as the reaction goes, and that is an exothermic reaction. You can always tell it exothermic because the products are more stable than the reactants. So the energy drops between the two. We don't look at the activation energy when we consider how much heat is produced by the reaction. Activation energy is to tell us how fast the reaction is. The change in heat, the delta H, tells us which side is favored, the left or the right. And in this case, the products on the right are favored. If we look over on the left reaction, this is an endothermic reaction. Endo means in. So now the heat is going into the reaction. What does that mean? That means heat has to be pumped in order to go from reactants to products. You have to add heat to the reaction. And you might say, well, wait, I'm warming it up. No, yes, you're adding heat to the reaction. But when you feel this reaction, it feels cold because it's literally removing heat from its surroundings. If you put an ice pack, one of these commercial ice packs that you buy in a drugstore, in your hand, and you smash that together, and you mix the two chemicals, this is an endothermic reaction. It literally is sucking the heat out of your arm or your shoulder or your elbow or your knee or wherever you're applying the ice pack to, and it's pulling the heat out. It feels cold to the touch because it's endothermic. It's absorbing heat in this case. So we have the distinction here. Exothermic produce heat, their delta H is negative, and you can tell the products are more stable, whereas endothermic absorb heat. The delta H in this case is positive because when I subtract product energy minus the reactant energy, I'm going to get a positive number. And so this always takes time for people to get used to. Delta H means absorbs heat. A positive delta H means absorbs heat. A negative delta H means it releases heat. And you can tell that because the product energy is higher. It's less stable than the reactants. And there are reasons why these reactions go, but it's beyond the scope of this course. So let's talk about catalysts. You probably heard the word catalyst, but maybe didn't understand what it meant. We briefly went over the definition in the beginning of this unit. A catalyst is a substance that speeds up a chemical reaction without actually being consumed by the reaction. In other words, it makes the reactants become products very quickly. Also, it makes the products go backwards to the reactants very quickly. So if you have a reversible reaction, it makes both of them speed up. In fact, a catalyst can make, if it makes the forward reaction increase by 1,000,000-fold, It'll also make the backwards reaction increase by 1,000,000-fold. But because a catalyst is not used up during the reaction, it can be used over and over and over again, and you only need to add a small amount of catalyst for a big reaction. So how does the catalyst work? Well, here's another energy diagram. We've got the energy on the y-axis and our reaction coordinate on the x-axis. We start with products and we start with reactants and end with products. And in this particular case, I made it exothermic, but it didn't have to be by any means. If you go backwards, it's an endothermic reaction, going from product to reactant. And so if we have this reaction without a catalyst, you have this activated energy state in the middle, what we call either an activated complex or transition state, and it requires a certain amount of activation energy in order to get to that, for the reactants to get up there. And once they get up to this hump, it's very easy to fall down, actually on either side. So this is why the reactions can go either way. It'll fall down either side. Most of the time it'll fall down to the right, become products, because in this case products are favored. But you have this reaction with a very high activation barrier, very high activation energy. But when you add a catalyst, what a catalyst does is it reacts with the chemicals temporarily, changes the mechanism of the reaction, and makes the new reaction have a much, much lower activation energy. Remember, lower activation energy means faster reaction. More molecules can get over the hump faster. And therefore, with a catalyst, it makes the activation energy lower. This is a much faster reaction. But I want you to note, if you were going backwards from the product to the reactant, this would be our original activation energy for the reverse reaction. That's without a catalyst. But now with a catalyst, it's only here. So the reverse reaction is also sped up when you add the catalyst to it. Actually, that should be reverse reaction. So both the forward and the reverse reaction are sped up, but the catalyst is released in the end and can be used over and over again, making all of the reaction go faster and faster. Enzymes are actually the word we use for biological catalysts. So these are molecules that you make. They're usually proteins. Most of your enzymes are made of protein, as well as some other things that might be attached to the protein to make them work better or make them work at all. And these are biological catalysts that speed up literally tens of thousands of different chemical reactions in your body. Without enzymes, you would cease to exist very quickly. So just a review, and this is really more for Chem 110 than Chem 100, but it's a good review anyway to go over the details. Size and shape and orientation. Well, we haven't talked in detail about this, but smaller particles will react faster, and they have to be oriented in the right direction. If a molecule hits another molecule on the wrong side of the molecule, and it hits it, it'll just bounce off, nothing will happen. Those are called ineffective collisions. But if they're turned around to face the right way, where the right atoms of one molecule slam into the right atoms of another molecule in the right position, that's a productive or effective collision, and that will give you an actual chemical reaction. Bulky groups might get in the way and prevent that. We call that steric hindrance. Again, this is not something you'll be tested on. Concentration. When you increase the concentration of your reactants, you'll make the reaction go faster. Why? Well, because there's more available. More particles are available. More of them will have the right amount of energy in order to produce these effective collisions and react with one another. Increasing the temperature will almost always, in some cases not, in most cases will increase the reaction rates. As you add more temperature, you're adding more kinetic energy. The molecules are moving faster. They're slamming into each other, not just harder, but more frequently, and therefore you'll get more and more productive collisions because you have sufficient energy. And then catalysts, as I mentioned, catalysts increase the forward and reverse rates, and they're not consumed by the reaction. And the reason they increase both the forward and reverse rates is because they change the mechanism of the reaction, and in doing so, they lower the activation rate. Lower activation rate means faster reactions. And with that, we'll stop here.